Is loud enough so that you can hear me and the video can pick it up. So I got lots of great questions over lunch. Some of you were there, some of you were not there. For those that were there, I hope I still have something interesting to tell you. But please ask those questions again if the answer isn't clear. So this is all based on work with Dave Morrison. And maybe I should just say that for me, the motivation in doing this is to understand the landscape away from weakly coupled limits. As we move away, do new things happen that are interesting? Can we control anything? And so forth. And that's something that I think about a lot. In particular, are there new features? Do you get any sort of, these would be great answers if and when the answer is yes. Great questions. Is there some interesting or compelling or broad new insight you get, and so forth? Is there some useful notion of genericity where that is a good question, but again, hard. So in recent years, in F-theory, which is not weakly coupled, which is sort of the other thing that I would have told you about today if I wasn't speaking about this. So I just want to mention some of the results. So there are new 7 branes that you can get in F-theory that you don't have in the weakly coupled 2B limit. You get more exotic n equals 2 subsectors, for example, Argyris-Douglas theories and the like. There are 7 branes that can exist for generic complex structure moduli, which is really a sharp definition of generic. I don't like being vague with words like generic, but genericity in moduli space is a well-defined notion. These are the so-called non-Hexable clusters, and there are strong arguments that they happen very, very frequently in F-theory. And one of the things that this implies, because these are strongly coupled configurations, it implies that nearly all of the moduli space of F-theory is strongly coupled. An interesting fact is that when you go to F-theory, there are new ways to realize SU3 and SU2 on 7 branes. That doesn't exist for any other SUN. And that's sort of part of the phenomenology side of the story that I've been looking into recently with Waddy Taylor and with Antonella Grassi and Julia Shanson. But that's F-theory. That's not what I'm going to talk about today. This talk is all about M-theory on G2, which is also not weakly coupled. And traditionally, this theory is hard. It's hard because traditionally there haven't been many examples. We don't have a full definition of M-theory. But it's getting better. One of the reasons is that there's many examples now. And the other is that people that have been doing F-theory have been taking an M-theory approach very far in recent years. And one of the questions is, with these examples and also in general, can we use those sorts of techniques to make progress with M-theory on G2? OK. Good. So in this talk by M-theory, I just mean 11-dimensional supergravity with wrapped M2 branes and M5 branes that couple into the supergravity C fields in the usual way. And part of the reason that I use these degrees of freedom is because they're easier to understand. And also, these are exactly the things that have allowed people to make progress in M-theory, F-theory duality in recent years. OK, good. So for me, this all started with what I consider to be a really, really great G2 math paper. Throughout, these authors are Corti, Haskins, Nordstrom, and Piscini. So when you see CHMP, these are the people. They use a construction called Kovalev's twisted connected sum, which is TCS, that will be used throughout. And basically, the point of this paper is that they had certain things called semi-Fano threefolds, which are particular 6-dimensional algebraic varieties, that can be used to mass produce compact G2 manifolds. And this is this paper from 2012, July of 2012, and I'm going to be talking a lot about it throughout. They've got other interesting things related to topology. For example, they construct some associative submanifolds. And if you do not know much about G2 yet, but are looking to get interested in it, to maybe even start working on it, this is a great paper to begin because it covers what to me seems like most of the basic elements of G2 manifolds in the math literature up until about 2012. So it's a really great introduction. It's about 80 pages. It's dense, but you can get through it. So, OK. So I mentioned at lunch that for me, this is just a formal inquiry right now because we really don't know enough about G2 compactifications or twisted connected sum G2 compactifications to make phenomenological or cosmological progress in concrete, here's your manifold, what does it give you type settings. Instead, I want to just discuss it quite broadly, and I want to be using compact models. I want to talk about gauge enhancement. So it's good to talk about here because there's been some G2 work historically here that's been going on, past and present. And I should say that also that for me, my entry into this from a mathematical perspective, I mean, I'm a physicist like most or all of you are. My math background is primarily in algebraic geometry. And one of the cool things is that algebraic geometry can actually be useful in these examples even though they're 7 manifolds and they're not complex algebraic varieties. Okay, good. So the outline is that I'm just going to review G2 manifolds. So the last time I gave this talk, I spent too much time on this section. So I may go a little quicker. I'm going to remind you what it is. I'm going to remind you what 11-dimensional supergravity and M branes, by which I mean M2 and M5, on them give. I'm going to talk about a G2 landscape, given those over 50 million examples, M theory on them, what sorts of 40 effective theories do you get? Ignoring KK modes. And I'll discuss the physics and give a concrete example. And then I'll talk about gauge enhancement. So M theory on manifolds doesn't give rise to non-abelian gauge symmetry, so you need to take singular limits in the metric moduli space in order to get gauge enhancement. And you can't use the standard Calabi-Yau trick, so I'll remind you of what the Calabi-Yau trick is, and also a suggestion for what one might do given that that trick doesn't work. So as an example, we'll talk about Coulomb branches of gauge theories and how they might be realized geometrically. And Coulomb branches have monopoles that are important, for example, the Polyakov monopoles. And instantons are, of course, also important. And I'm going to try to tie these gauge theoretic notions together into a geometric setting with G2 manifolds. And we'll get some interesting structure. So, yes?
Do people talk about G2 manifolds with Kavli?
Oh, I don't know. So maybe they do, but I haven't heard about it.
Okay.
Yeah. Good question. Okay, good. So this is my G2 review. It's going to be even faster than the last time I gave this talk. And in fact, it's only going to be 3 slides. So, good. So a G2 manifold. G2 is an exceptional Lie group with rank 2 and dimension 14. And a G2 manifold X is a 7 manifold with holonomy G2. 2 critical things. One is that this is not a complex algebraic variety. The dimension of the manifold is 7, which is not even. So it can't be a complex manifold. There's no Yau's theorem, by which I mean there's no simple topological criterion that you can check that allows you to say, yes, this has a Ricci flat Kähler metric. Sorry, not the analog of that, a G2 metric. So in particular, you can't use complex algebraic geometry, and they're much harder to construct because there's no analog of Yau's theorem. So these are characterized by G2 structures that determine a metric G phi and a G2 3-form capital phi that I'm going to be talking about throughout. And in particular, there's only one type of metric modulus. They're the moduli that are coming in this phi, this G2 form. And so the following are equivalent. The holonomy is contained in G2. Phi is torsion-free, and d phi and d star phi are 0. Those 3 statements are equivalent. And in particular, that's contained in. So the holonomy is exactly G2. If and only if these things are true, and X has finite fundamental group. Okay. So G2 calibrations will play an important role. So G2 manifolds have calibrated submanifolds. This is a famous notion of Harvey and Lawson. In particular, there are so-called associative 3 manifolds and co-associative 4 manifolds. And these are volume-minimizing representatives of the homology class. In particular, even though you don't know the metric, you can still compute the volumes of these submanifolds. That is one of the distinguishing characteristics of calibrated submanifolds, period. In particular, these ones that exist in G2 manifolds. So the volume of an associative, M3, is just integrate phi over the manifold, and similarly for the co-associative, M4, integrate star phi over the co-associative. So one of the reasons that I'm mentioning this is Corti, Haskins, Nordstrom, and Pacini gave the first construction theorem for compact associatives and compact G2 manifolds. And a rough statement is that there's a rigid one associated to each rigid holomorphic curve in an appropriate building block that I'll tell you about. And furthermore, there's a non-rigid one for each appropriate slag, special Lagrangian submanifold in the building block. So these are the calibrations. So 11B supergravity and M2 branes on a G2 manifold, not a singular case. This is giving you a 4D n equals 1 theory, which is why part of the reason why we're interested in it. So KK reduction.
Dumb question.
Yeah.
You said you don't know the G2 metric?
Yes.
Isn't there a formula for this thing in terms of the calibration of the cycle?
There is, but we don't ever write that. Sorry, the calibrate. You mean the G2 form? There's a formula for it in terms of the G2 form, but we never write down the G2 form explicitly. The G2 form is this 3-form phi.
Yeah,
That's right. Yeah. So right, exactly. Yeah, but that's right. We don't write that down explicitly. We know the exception.
Phi.
Right. Yeah, right. Exactly.
So you know those integrals over the calibrated 3 manifolds,
Exactly.
but you don't know phi and you don't know.
That's exactly right.
Just like the Kähler form of the Calabi-Yau.
Exactly. Exactly. Yes. So that's exactly the right way to think of it. It's sort of a G2 analog of the Kähler form and holomorphic curves. Good. So when you KK reduce supergravity on this, you get V2 of x abelian vector multiplets, and you get V3 of x massless uncharged chiral multiplets. If there's submanifold representatives of certain classes, you can wrap M2 branes and M5 branes on 2 cycles and 5 cycles to get charged particles. Their charges can be computed by intersection theory, just topological intersections on the manifold. And you can also get instantons, domain walls, strings, etc. from wrapping the M branes. And the key is that you get at most abelian gauge symmetry, which is why we're interested in this, how to take a singular limit to get non-abelian theories or even abelian theories that have massless charged matter. Yes?
So you mean abelian manifolds?
Pardon?
So manifolds, are they space-time manifolds or manifolds in G2?
So which manifolds?
Charged.
These ones here. Yes, they're space-time manifolds.
So they're abelian manifolds.
Exactly, they're abelian manifolds. But for example, you might say, suppose this smooth manifold is representing a Coulomb branch of some non-abelian gauge theory that's represented in the singular limit. We'll see that it is known particularly in M-theory on Calabi-Yau that the parametric dependence of the Topf-Polyakov monopoles on the Higgs Vev and the gauge coupling can be seen geometrically. So they're abelian monopoles, but you can think of them via movement in moduli space sometimes as associated with symmetry breaking. So good. So smoothing this singular limit is the Higgs mechanism, and so the reverse question is how do we reliably un-Higgs? And there's lots of local work that's very interesting. And the basic story is that non-abelian gauge symmetry, vector-like matter, and chiral matter arise from codimension 4, 6, and 7 singularities, respectively. Okay. So a landscape from twisted connected sum G2 manifolds. Any other questions on the background before I move on? That's just sort of the setup. Those are the physics ingredients that I'm going to bootstrap in. Classically, I mean that this is a classical landscape on smooth G2 at large volume. It's really an 11D supergravity landscape, but I don't think anyone's going to take issue with that. So there's been huge math progress on these manifolds, and so there's a question, what does M-theory on them give you? What can we learn about the landscape? What is there still to be done? Are there places where the choices that the mathematicians make us think that it was one way physically when it could have been something much more general, questions like that. So this is the Kovalev twisted connected sum construction. And the question is, how do we use the twisted connected sum construction to get a G2 manifold? So the basic idea is to appropriately glue to appropriate building blocks, M plus minus, and X inherits a G2 structure from these building blocks and then show that it's torsion free, because that gets you that the holonomial is contained in G2. And then, in fact, these manifolds have trivial fundamental groups, so in particular, it's holonomial G2. So M plus minus is a 7 manifold that's, I'm getting way ahead. This is what I'm looking for. M plus minus is a 7 manifold that's some 6 manifolds times a circle, where V is a particular type of 6 manifold called an asymptotically cylindrical Calabi-Yau threefold. What that means is that asymptotically, as you go towards one region of the manifold, it starts to look like C star times a K3 surface. And this C star has a coordinate C that we write in terms of T and theta this way. And in particular, this gives rise to a natural G2 structure on each asymptotic n that takes this form. So for example, omega s is the Kähler form of the K3 surface, and so on. Theta, capital omega is the complex structure. And the basic point is that you have 2 K3 surfaces associated with these M plus minus, and if you were to glue them in an appropriate way, such that the G2 structure was invariant under it, you would be able to build a nice G2 structure on the total space, which is compact. And then if you could show that that was torsion-free, you would have a G2 manifold. So that's what it is. And in fact, this structure here, if you do this mapping, phi, t, theta, and s, S is one of the K3s, sigma is another one of the K3s. Notice that you're swapping the coordinates phi and theta. There are 2 circle coordinates because it's C star times S1 asymptotically. So there's an S1 that comes from the C star, and there's another S1, and you swap those circles. That's why it's not holonomy SU3, it's holonomy G2. If you didn't swap them, you would have holonomy SU3. Good. So the point is that this map leaves phi invariant. And it's not going to play a critical role in physics here, except for the fact that it gives us the construction. Pardon?
Why wouldn't it be holonomy SU2? It's like K3 times cylinder.
But the full, yeah, but that's just asymptotically that it looks like K3 times C star. So the full space is a Calabi-Yau free form. Good question. Good. So Kovalev's theorem, this is the key observation for the gluing, that you get that natural G2 structure on the space. So in particular, the diffeomorphism that you use to glue has to satisfy these properties that makes the G2 form invariant. And there's this gluing map that swaps the circles. S1 minus becomes S minus becomes S plus, and S plus becomes S minus. It's this important swap. And basically the point is, this theorem is given such M plus minus a gluing map, and gluing maps in this diffeomorphism on the K3s, you get a twisted connected sum 7 manifold X. And what Kovalev showed is that there's a deformation of that natural G2 form within its cohomology class that is torsion free. And that is sufficient to have a G2 manifold. So this is the theorem, this is the setup. And the point is, I just gave you some story where you could say, what are the possible M plus minuses that I can write down that allow these properties to hold so that I can construct G2 manifolds? And you might imagine that mathematicians are very clever, and over time they construct broader and broader classes of M plus minus to get these G2 manifolds out. So in particular, Corti, Haskins, Nordstrom, and Cassini are very good at this, and they've done it in about 50 million examples. And their progress is to use asymptotically cylindrical Calabi-Yau manifolds that are obtained from cutting a K3 surface out of what's called a weak Fano algebraic threefold. And the fact that it's weak rather than just Fano is a slight generalization that allows them to get from smaller numbers up to 50 million.
Co-twisted connected sum because you're taking the connected sum of two K3s and you're twisting it with this circle.
I'm taking the connected sum of M plus minus, really, which contains the K3s, but it's
right.
twisted in the sense that it's swapping the
swapping
K3s.
Okay.
Exactly, exactly. Yeah, very good, very good.
So which topological invariants is very complete of this? I mean,
Very good, yeah.
Are they, are there some classes where they are the same, or are they always different? Are there 50 million different, B3s or number groups, or what?
Good. So I don't know. I don't think they even say to what extent they compared the topological invariance of all of them. Many of them are different, and in particular, the reason why you can get to such large numbers is because the topology on one side and the topology of the other side could be different, and if you have different topological building blocks that determine the topology of the G2 manifold in different ways, it allows you to get large multiplicities. I don't think that they said anything about, of this 50 million, we are sure that this many are independent.
But do they compute B3 groups?
Yeah, that's right. The integral cohomology is known for all of these.
What's the rough range of these?
Oh, good. I don't say anything about that anywhere in here, actually. I don't know. I mean, I think like 100 to 1,000, but I'm not sure. I don't.
But not ridiculous.
Not like for Calabi-Yau fourfolds, as far as I know. Yeah. But, yeah. So that's this construction, and we're going to use it. So in particular, you are just asking about topology. So the topology really matters for physics. So if we have V plus minus constructed from other algebraic threefolds Z plus minus by cutting out this K3 surface S plus minus, in particular, these Z plus minus are K3 fibrations over a P1. And then you cut out the K3 surface at infinity. And there's natural maps from the second cohomology of V plus minus into S plus minus, and maps have kernels and images. So we're going to call the kernels K plus minus and the images M plus minus. So then the second and third cohomology, this is, I didn't tell you the full structure here, but the second cohomology is identically this, where N plus intersect N minus plus K minus is the second cohomology of the G2 manifold. This is computed, and in particular, it's related to things that, this is stuff that is glued at the middle, and this is stuff that sort of exists away from the middle where the gluing is happening. And that can be made precise. But the reason why I truncated H3 is that I just wanted to show you that there are things in the kernel of this map, two forms on V plus minus that are trivial in here, this K plus, that contribute not just to H2 of the G2 manifold, but also to H3. So you're having one algebraic origin of both non-trivial 3 cycles and 2 cycles, sorry, 2 forms and 3 forms in the G2 manifold. Poincare duality, if it's ever unclear what I'm talking about, will be implied. So there's also a theorem, if you have a rigid holomorphic curve in V, then there's a deformation of C times S1 that's with a rigid associative in X. So these are the sorts of theorems that one's interested in for physics, and I'll get to why in a minute. And so that's the topology of these twisted connected sums. And part of the beauty of it is that you can actually get your hands on these things in algebraic geometry and then bootstrap that to information about the G2.
Is V plus minus on topic? Is S plus minus the definition retract of V plus minus?
No, S plus minus is a K3 surface.
I think I don't understand what V is. I thought it was a cylinder over
V,
S plus minus.
good. So Z plus minus is a K3 fibration over P1. And I have the north and south pole of the P1. And call the north pole infinity. There's a K3 fiber associated to every point on the P1, and I can cut out one particular one of them. So Z plus minus is that thing, and then I cut out the K3 surface at infinity, which gives me this non-compact thing that asymptotes to K3 times Z star. Good. All right, so just broadly, if you put M theory on these, the known manifolds, one thing that's true is that X is a vacuum with broken non-abelian gauge. Sorry, if it's true that there's a singular limit that gives non-abelian gauge symmetry, nearly all of these are Higgs branches. What I mean by this is that the semi-final building blocks of Corti, Haskins, Nordstrom, and Cassini, the one that allowed them to generate the large numbers, they made some additional assumptions, and one of them is that K is equal to 0 for one of the halves. So if you glue these, and moreover, the simple gluing, which takes n plus intersect n minus to be 0, all of this in the topology adds up to the fact that this is 0, and that's 0, so the second Betty number is 0 for nearly all of these examples. This was based on choices that allowed them to mass produce the cases. It is, I don't have any reason to think that that is what should be true broadly in the physics, but it's just easier mathematically to construct those. But that's the current status. Oh, it was right there. Fluxes never have to be turned on in these. Remember that there's a flux quantization condition in M theory. It's that the G4 flux in M theory plus 1/4 of the first Pontryagin number has to be in the integral cohomology. And in particular, it's always Beasley and Witten and maybe people before them, but certainly they did at the very least, showed that the first Pontryagin number is such that P1 over 4 is always in the integral cohomology. So you could choose to not turn on G-flux. This is in contrast to M theory on Calabi-Yau, where you often are forced to turn on G-flux based on the topology. So that's interesting. So instantons, due to Corti, Haskins, Nordstrom, and Cassini having these rigid associatives, for the first time you can talk about M2 instantons that don't have deformation modes. By that I mean that the rigidity is exactly related to the fact that there's one of these and they don't come in families that you can deform around in the G2 manifold. They're diffeomorphic to S2 times S1, so you have to be concerned about Wilson line modulini of the instantons that, depending on the other details, may lift the superpotential correction. But I don't have anything to say about that now. So, and finally, some G2 transitions can be understood in the topological transitions that occur in the threefolds on the ends.
So if you decided to turn on fluxes, would they have any effect whatsoever on the physics? The question is precise. Would they affect anything?
So I am sheepishly forgetting a little bit of the paper about Beasley and Witten, but I believe what they were interested in was flux superpotentials. Flux superpotentials.
Oh, so they turn on the fluxes.
Pardon? They turn on the fluxes, and I believe that
They
one
are
of the
superpotential.
you get a superpotential.
Oh.
Exactly, like Kugo and Raffleman. There's one part of that I'm confused about, which is why I say sheepishly. But yeah. So Chris is my colleague. I should really know. He's a great guy. But yeah, that's right. But one of the things that's critical in M theory and Calabi-Yau is that sometimes you just have to turn it on based on the topology, or else there's an anomaly, and that's not the case here.
Is there a discrete symmetry that all this is showing? Is there like a Z2 that swaps the two sides of these constructions?
Oh, no, because they can be topologically very distinct on both sides.
Good.
You could have one M plus minus and one M plus, and the one M plus, one M minus that look totally
So
different.
the typical vacuum construction doesn't have any.
Exactly. I should say that one of the reasons why I mention this is that some of the effective supergravity theories that people use G2 to motivate assume fluxless M theory compactifications on G2 manifolds. And as someone, when I was learning this, I asked myself the question, is that legitimate at all? Because we know in M theory and Calabi-Yau sometimes you're forced to turn them on. That is never the case in G2, but on the other hand, choosing the fluxless choice is choosing the origin out of a large lattice of possibilities, subject to consistency conditions. All right, so yeah, that's good. Good. So here's a U1 cubed example that Dave and I studied explicitly. Study physics using the topology of these manifolds is the idea. So in this example, K, which contributes to the second cohomology, is 3. It was non-zero because the threefold that we chose to cut up the K3 surface out of was what's called a non-generic anti-canonical pencil. And in particular, it means that the pencil, one of the things that generates the pencil is this very particular quartic. That's just the product of x0, x1, x2, and x3 and p3. And this gives you extra topological structure. The fact that it's a non-generic anti-canonical pencil, where one of the generators is this non-generic quartic. So once you have this G2 manifold, you can just compute topological intersections. And in particular, you can compute the G2 intersections via the intersections in the 6 manifold for these cases. And you have a bunch of holomorphic curves that become honest 2 cycles in the G2 manifold, and you can wrap M2 branes on them and compute intersections, and get an interesting spectrum of U1 charged particles, U1 charged vector pairs of chiral multiplets in 4D.
What's the size?
Oh, those are the fields. Those good. So the different subscripts here are associated with how they're occurring topologically. It's really not, the notation is not critical for what I'm telling you now. But the point is that there's a bunch of different origins of them. And so these are chiral superfields in your 4D effective theory that have particular charges, where the particular charges are determined topologically. Okay. Okay, so we're going to use this result again. So anyways, just to say where I'm going in a minute. With these, you could say, suppose I shrunk down one of those curves in some consistent way, and I have some state becoming massless. And I then Higgs it and predict something about the topology of the deformation. So we use the results again, in particular for instantons. So given a rigid holomorphic curve in V, there is a natural free cycle in G2 manifold M coming from the circle product. This gives rise to a 3-cycle class in the twisted connected sum that has a rigid associative representative. So Harvey and Moore showed that M2 branes on rigid associatives can correct the superpotential. In particular, they were focusing on the case that V1 of the associative is 0. That's not the case here. And there's extra physics one has to do to study that case. But suppose that those were that the Wilson line modulini weren't an issue in that case. Then you would have a superpotential correction of this form, which is the sort of thing that you expect from TEM2B or F theory expectations, where you can have multiple different chiral superfields appearing in the exponentials, and they can play off each other kind of like in a racetrack. So, and I mentioned this about Wilson line modulini. So, good. So we also did a circle of conifolds transition. So in the Columbia.
Why was the other one so symmetric?
Pardon?
Why did you have such a symmetric table of charges previously?
Oh, sorry.
Should we read it off from here too?
No, you can't. You mean this? Sorry. The transitions are good.
Yeah, it looks like there's a lot of symmetry in these 2 blocks.
There is. It's determined from topological intersections, and the classes are related. So for example, if you have a curve in the class sigma 1, a curve in the class sigma 2, and a curve in the class sigma 1 plus sigma 2, then the charges are going to be intimately related according to the homology relation. So that sort of thing is just the sort of thing that can happen. Well, and it should be the case because things are often symmetric for the, well, okay, so these are, this is non-chiral matter, so anomaly cancellation doesn't come in here in that way, but the intersections often show up in somewhat symmetric ways. So for example, in resolutions of elliptic vibrations, Cartan matrices are what are associated with certain modes of the intersections. Okay, good. All right. So the circle of conifolds transition. Remember the Calabi-Yau case. So the Calabi-Yau conifold, you take a massless particle limit by calibrating a 2-cycle to 0 by movement of the Kähler moduli. And in G2, you can't do that so simply because there are no calibrated 2 cycles. The reason why it worked in Calabi-Yau is you had a calibration, you can compute its volume even though you don't know the metric, and you can move in that moduli space and shrink it down. But one thing that you should remember is the topology of these things. You get a non-trivial contribution to H2 from K+, and also a non-trivial contribution to H3 from K+, and similarly for K-. In particular, we have K non-zero, so the second and third cohomology are related. Particularly, you can think about the Poincare duals. The point is that the rigid associative, K, actually I didn't say this here, I should. You get a rigid associative here because of a rigid holomorphic curve in one of the V's that contributes to K+, which therefore also gives rise to a rigid associative, and this is related to this contribution to the higher cohomology. So you should think of this manifold as an S2 fibration over an S1, where you want to collapse that S2, but you can't control that S2 volume directly via some calibration, but you can control the volume of the associative. And in particular, you can take this limit where this S2 fiber of the S1 shrinks down. And then you could also say, okay, well now that I've done this, after you shrink the two-sphere in the Calabi-Yau conifold, what you want to do is deform it. And you can do this here too. I should say it's a circle of conifolds, not just a conifold. Conifolds are codimension 6 singularities, so in a 7 manifold you're getting a circle of them. But you can deform these, and the deformation also gives rise, if you get an S3 slag in V, then it's associative in X. So you're doing something very similar in the G2 manifold to what you would do in the Calabi-Yau case.
Sorry, can you explain that again? What is a super-conifold transitions?
Yeah, that's right. So in the Calabi-Yau case, the conifold is a point in the Calabi-Yau threefold, which is a codimension 6 singularity. In this case, you have the structure that you have is a two-sphere, a rigid two-sphere times an S1, and the two-sphere shrinking down over the entire S1. So you have a circle full of conifolds. Rather than a single conifold point, you have a circle of conifolds. And it's still a codimension 6 singularity. So the codimension hasn't changed. It's just that the dimension changed. And so you get this one parameter family of conifolds. Yeah. Okay, good. So in the conifold transition, what you're doing is you have a charged particle becoming massless, and then you Higgs the theory. And when you Higgs the theory, you're changing naturally the charges of the things according to the Higgsing, the charges of the particles, and that has to be understood from the topology of the deformation. Just like we understood the charges from the topology of the resolution, we understand the charges in the Higgs theory via the topology of the deformation. Oh, I don't have a slide on that, I guess. Okay, so I'll tell you the result, because I thought I was going to have a slide on it. It all goes through. The point is that you can do this circle of conifolds transition where you shrink it down and then you deform, and you have reduced the U1. Instead of having 3 U1s, you now have 2, and the topology exactly matches what you would expect from the field theory. You Higgs the field theory, the charges of the Higgs theory have to show up in the topology of the deformed manifold, and it works. Okay, so gauge enhancement, how do you get it globally? So families of metrics in non-compact examples, they're really great, but we can't do that in this case in compact examples because we don't know the metric. And what we want is a language or approach that you could, with our results now and with further results in the future, apply in compact examples. So I don't want to use a local language. I want to use a global compact language. So in particular, in the last example, we ran into an important problem that I didn't emphasize that much. I mentioned it much, but it's really a problem, and so I want to say it. The problem is made evident by using analogy to M theory on Calabi-Yau. So why does gauge enhancement work for M theory on Calabi-Yau in the simplest case? And what is the G2 obstruction? So the Calabi-Yau singularities are well understood because we have defining equations in complex algebraic geometry and so forth. You write down an equation, you take appropriate derivatives, you see that it's singular. And in particular, you know how certain singularities relate to families of 2 cycles going to 0 volume. You know that as you move in the moduli space in a particular way, a particular 2-cycle shrinks and develops a particular type of singularity. And you're calibrating a curve to 0. In particular, the dimensionality of the family of curves that's shrinking determines the space-time quantum numbers. This is written Aspinwall, Katz, and Morrison. So that you not just say that I have a charged particle of this charge becoming massless, you also say you can also say things like this is a vector multiplet or a chiral multiplet, but obviously not both. And that depends on the dimensionality of the moduli space of curves. Good. So by varying J and studying this dimension, you can really identify the charges and the space-time quantum numbers of the matter that's becoming massless. And the whole problem is that you can't do this in G2 because you don't have calibrated 2 cycles. So the proposal that Dave and I put forth was to use the calibrations that you have, which is 3 manifolds and 4 manifolds, which worked in our last example. So the associative 3 manifolds and co-associative 4 manifolds are calibrated so you can control their volumes as a function of moduli. And in particular, we define cones of associatives and co-associatives that are analogous to the Kähler cone. And the idea is to get singularities by collapsing on those calibrations. In one sense, it's a math trick because you can collapse the 2-cycle within them. Remember in the conifold example, we had a 3 manifold that was an S2 vibration over S1. And in the limit, we collapsed the S2 fiber. So you have a massless particle. And the physics option is that you might say, okay, but there's other signatures of symmetry breaking. Massive W bosons are not the only signature of symmetry breaking. So for example, the mass of the W boson goes like the gauge coupling times the Higgs value, but there's monopoles too that go like that with G, and there's vortex strings have a V squared factor, and you might say, why don't we use defects rather than W bosons to study symmetry breaking? And in the other direction, in the singular limit, un-Higgs. Okay, so some defects can arise from calibrated cycles, and some from not calibrated cycles. So for example, strings, instantons, and domain walls can come from wrapping M-branes on calibrated cycles, but monopoles, for example, come from wrapping a 5-cycle, an M5 brane on a 5-cycle, and that is not calibrated, but they're still useful. Okay, so what we want to try to make certain aspects of this proposal of shrinking 3 cycles and 4 cycles for the sake of gauge symmetry manifest, we want some natural 3-cycle or 4-cycle that is somehow associated with symmetry. And there's a lemma of Joyce that I thought that originally this was going to be like the main part of the answer, but it's not. But when you learn why you're wrong, sometimes you learn why it's useful. And there really is something here that I think is really interesting. And the lemma is this, and I'll say the math before I get to the physics. So if you have a manifold X with holonomy exactly G2, consider any non-trivial class sigma in H2. Then sigma cup phi, the G2 form, is less than 0. And there's an orientation you could have set phi to minus phi and swap things around. But the point is that it's not 0. The point isn't the orientation. The point is that it's not 0. So in particular, to any such class, you have an associated U1 in M theory because it's a contribution to the second Benny number, and you reduce the M theory 3 form along that harmonic form, and you get a U1 in the 4D theory. So for putting in physics language, for any U1 in M theory on a 7 manifold with exactly G2 holonomy, you have not just the non-trivial 2-form class, but sigma cup sigma also has to be non-trivial, a non-trivial 4 form. And its Poincare dual has to be a non-trivial 3-cycle. Poincare dual of sigma cup sigma. So I'll call this D lower sigma throughout. So this is significant because it's something that's totally general for an M theory compactification on a smooth G2 manifold. U1s always have this property. And so if you ask the question, okay, this is a class, but you're not guaranteed for a homology class that you have submanifold representatives of that class. It may or may not be the case. This class always exists for any U1 in M theory compactification. And we want to ask, what if there was an associative submanifold representative of D sigma? Is this class interesting physically? And could you calibrate that to 0 for gauging answer? And the answer is no. So that's the limit of infinite gauge coupling. So when you just when you reduce the 11D Sugra action and study, even in the case of a single U1, and study what is the G2 contribution of the G2 space to the 4D effective gauge coupling, it goes like sigma wedge star sigma. But there's a nice theorem for 2 forms of G2 manifolds, a nice identity, I guess, that allows you to replace star sigma with negative sigma wedge phi, the G2 form. Okay, so this is the gauge coupling from 11D Sugra, and then I use this simple identity, but then I can do Poincare duality to turn this into phi integrated over this D sigma class. Okay, so and in particular, if this is an associative representative, that's the volume because it's the calibration. So what we found is that there's a particular class that if it has an associative submanifold representative, the volume of that submanifold computes the gauge coupling. Totally, for any M theory compactification with this property.
Is this map from 2 cohomology to 3 homology with no sigmas on D sigma? Is that map injected? I mean, do you have 2 different U1s that gave you the same set?
Great question. Yes. So I don't know of a case that exemplifies it, but I think that physics requires it. Imagine that you have an M theory compactification where you're on a Coulomb branch where you've broken G to U1 of the rank G via an adjoint chiral bev. There you have rank G U1s. But in the limit that you shrink it all down, you should have all of the P1s collapsing, and in particular, you should have a single 3-manifold there because the gauge coupling unification has to occur within a singular limit. So there should be a single 3-manifold there, that is, which therefore has to have the same homology class.
Right.
There's not different homology classes. So that's right. So I think in cases where you're breaking a non-abelian theory, you'll have to get, you might have sigma 1 and sigma 2 associated to breaking SU3 to U1 squared, but then the classes may be the same if they're enhancing in the singular limit. I think that that's more or less a requirement. But well, I was going to say, the Joyce example I'm going to show you is an SU2 example, so it doesn't exemplify that. But maybe he has an SU3 example that works. Okay, good. So the upshot, first of all, because this volume is positive, according to this identity, this inequality, so you have a finite gauge coupling, and if d sigma exists, you could also wrap a gauge instanton. You could wrap an M2 ray on that submanifold and have an e to the minus 1 over g squared type correction, reduce the gauge coupling. Good. So I want to deduce additional features of X from physics and then see what to calibrate based on doing that. So I'm going to just go gauge theory for a second. So if I just break G to U1 to the rank G, for G is simple Lie group, well, the W bosons, of course, got a mass, but the Z bosons remain massless. We've got to talk about how to do this geometrically. And in particular, you have a tough polyacrylic monopoles that are measured by pi2 of G mod H, and the critical monopole, the one that satisfies the Vogel-Money bound, the dependence of the monopole mass on the Higgs value of the gauge coupling goes like d over G. So for a G gauge theory, for G has gauge instantons, of course it's measured by pi3, and there's an instanton size, the modulus rho, and it's suppressed by e to the minus 8 pi over G squared. And even when you break G to H, G instantons play a role. This is this so-called a Tuff term, which generates a correction to the instanton action that depends on the Higgs vev and the instanton modulus. But in fact, in that limit, rho is not a modulus anymore, but there's still this constrained instanton formalism of Affleck that allows you to study these cases. So my point in saying that this is even in the broken theory, there's all sorts of interesting other things that should be coming along for the ride physically. So how would you get that in M theory? So how, if you had that sort of gauge theory realized as an M theory vacuum, how would you get it? Okay, so I'm gonna make some assumptions based on the only way that I know how to realize these things. So I'm going to go to a specific case, this non-phenomenological Georgi-Glashow model, which was the first sort of model to exhibit the polyacrylic monopoles. And so I'm going to break G to U1. I'm going to break SU2 to U1 with an adjoint scalar vev. In a sense, this is like n equals 1 Seiberg-Witten. So it's sort of like the Coulomb branch, n equals 1 Coulomb branch version of Seiberg-Witten. And in particular, I have a couple of topologically non-trivial classes on the G2 manifold. Suppose that X, the G2 manifold, realized this sort of vacuum. Well, you need a non-trivial 2 cycle, a non-trivial, by duality, you have a non-trivial 5 cycle. But remember, there's this whole Joyce thing that gives me this non-trivial 3 cycle also. Okay. But that's not all of the physics that we need to recover this sort of gauge theory. So I'm going to say, it is true that the only origin I know of these things in M theory is to wrap M grains on various submanifolds and get these sorts of effects. To wrap them, you need to have a submanifold representative of a class. You can't just wrap it on anything. You really need the thing to be there as a submanifold, a positive volume thing. And so we need W bosons, monopoles, and instantons. And I'm going to assume that I'm getting them from wrap grains. So in particular, these classes are the things that you have, and I'm going to assume that there are submanifold representatives of these classes. 5-manifold, 2-manifold, 3-manifold. And in particular, the instanton behavior that you expect, the basic scaling, follows from the fact that in supergravity, the volume of this particular one that follows from the Joyce limit goes like 1 over G squared. Okay, so we have 3 volumes of 3 submanifolds, the 2-manifold, the 5-manifold, and the 3-manifold. But this Higgsing, we have a gauge coupling and we have a Higgs vev. And it seems like this is an over-constrained system. But in the gauge theory, the monopole mass goes like G Yang-Mills times V, the W boson mass. And that's coming from an M2 grain wrapped on this 2 cycle. And the monopole mass is from the M5 grain wrapped on the 5 cycle, sigma twiddle. And the gauge theory dependence goes like V over G for that. That's this volume of this submanifold. Okay, and you say, all right, well, these things have the same sorts of parameters appearing. And in particular, you know that the gauge coupling is computed by this d sigma. So the monopole mass goes in a particular way like Bev over G, which looks like MW over G squared, which looks like the volume of this 5 manifold, just by the fact that the 5 manifold is where we're getting the monopole from in the first place. But based on this parameterization and how it relates to the volumes of the other manifolds, it also looks like volume of the 2 manifold times volume of the space. And this is the structure that you expect of a fibration. I mean, certainly in the case of a product, if you have a 5 manifold, it's just an S2 product times a 3 manifold, the volume is just the product. Similarly for a fibration, if the fiber moves with finite volume, with continuous volume along the base. So this volume relation that you expect from the gauge, this parametric gauge theory realization gives rise to this G and V type of equivalence that suggests a volume relation that you should think of this sigma twiddle, this 5 manifold, as P1 fiber, as S2 fibered over this 3 manifold. Okay. So part of the reason that you land on this and it's not crazy is that the same exact thing happens in M theory on Calabi-Yau. So M theory to 2 dimensions on an elliptic Calabi-Yau fourfold, for the sake of time, I'll just say it. When you resolve this thing, what you get is a 6 manifold that is fibered by P1s over a 4 manifold. The gauge coupling is computed by the volume of the base. The W boson is computed by the volume of the fiber, and the monopole comes from wrapping the whole thing, and so all of these things have to be intimately tied together. And in particular, in 2+1, you really, of course, have BPS monopoles. And this story really goes through. The interplay between the volumes appearing in this vibration of the base, the fiber, and the total space match exactly what you expect in the gauge theory. Okay, so anyways, the point is that we're getting a very similar picture here based on this critical Joyce-like relation. So by rather general global G2 and Coulomb branch considerations, what we've landed on is a fibration structure, and this is expected from the standard picture of S2 fibrations over a 3 manifold that people talk about in G2 compactifications. But we got there by quite general techniques, making some assumptions to say that if M theory realized this type of physics, here's the extra structure. Okay, so what to calibrate to 0? The story that I told you had an adjoint chiral just in the gauge theory, and I haven't mentioned anything about that from the point of M theory. So if we're going to get a singular limit where we have some 7-dimensional gauge theory that we then take down to 4 by a compactification of d sigma, one of the ways that you'll get adjoint chirals is if this d sigma has 1 manifold in it, has 1 cycles. So if P1 of d sigma is non-zero, what you get is a 2-sphere fibration over each 1 cycle. So this picture, before I introduced adjoint chirals, is the picture of these. This is a 3 manifold, and these are 2 manifolds. So this whole thing is a 5 manifold. If I need adjoint chirals in the story, I need 1 of the manifolds in here. So I could shrink this 3 manifold if it had a calibrated representative, but that's the infinite gauge couple limit. That is not what you want. On the other hand, you have, because of these adjoint chirals, you have these 3 cycles associated with the S2s over the S1. And if you had an associative representative of that, you could shrink it down. And in the same way, I don't think we have an example that realizes this. In the same way that the circle of conifolds shrunk the 2-sphere fiber of a 3 manifold, you can imagine that happening here to give rise. No, the Joyce example does do this, to give rise to the sort of structure you want. But this is a pretty general argument. I mean, I didn't really do much here except make a few simple physical assumptions, saying what if M theory realized the gauge theory like this? How would you expect it to arise? And I landed naturally via this Joyce lemma on this very natural vibration picture. That is what we know to be the case in M theory on Calabi-Yau and what we expect to be the case, certainly from the codimension 4 picture of G2 singularities. Okay, so good. And in particular, so Joyce's examples give SU2 to U1, and we did this in our paper. And basically, in that case, I'm attaching physics language to what Joyce did. Joyce had a T7 orbifold by some discrete group. What he does is he has a process by which those things are resolved. You have an A1 singularity that's resolved, and he shows that that family has a G2 metric. And in particular, in the singular limit, this d sigma, this 3 manifold over which you have these spheres shrinking, is a T3. So you have 3 adjoint chiral multiplets in that theory because B1 of T3 is 3. And you have exactly this structure where you have this manifold T3, whose existence is guaranteed by the Joyce lemma, but you have these other vertical 3 manifolds with 2 spheres fibered over S1s that are shrinking in the limit. So and Dave and I had this proposal to use 3 manifolds and 4 manifolds to get gauge enhancement, since you can't calibrate 2 cycles directly. And we're seeing that it's a fairly natural structure. Okay, so one of our dreams for obtaining singular limits with non-abelian gauge symmetry. I have another slide? No. Okay, good. Then I will say this. So in the twisted connected sum story, the only thing that I showed you so far was one example with a circle of conifolds, which is massless charge matter that is not non-abelian gauge symmetry. So topologically, the reason that we were able to get a handle on that was because you had a 2-cycle class in one of the building blocks that corresponded to a non-trivial contribution to K+, that embedded into H2 of the G2 manifold and also H3 of the G2 manifold. So you have this topological structure appearing in 2 places in G2, even though it only appears once in the building block. So the natural idea, given that these building blocks are K3 fibered, is just to shrink the 2 cycles in the K3 in the way that you normally would to get an ADE type similarity. It's hard to do that. One of the reasons is that those would be things that would have to be, so if you were on a Coulomb branch associated with that story, those K3 2 cycles would have to be sitting in n plus intersect n minus, but nearly all of the examples explicitly set that to 0 because it requires some lattice algebra to get the looming to work correctly. You could imagine that you had a Higgs branch where what you had was a 2 cycle in the K3 that was non-trivial in the K3 fiber of this G2 manifold, but was trivial in the total space. That would be what a Higgs branch would be. So our idea basically was a way to, we don't know it yet, but it was based on a topological correspondence between what's happening in the topology of the building blocks and sort of the quote-unquote Higgs branch topology of the G2 manifold. And the idea was that if you had a calibrated submanifold of those certain classes, you might be able to shrink 2 cycles in the K3 fiber and get non-abelian gauge symmetry, singularities along the 3 manifold. Anyways, so there's 50 million compact G2 manifolds. I can't spell apparently. And this is an 11D supergravity landscape, and nearly everything there is Higgs branches. If a non-abelian gauge enhanced limit exists, they're nearly all Higgs branches because V2 is 0 for nearly all of the examples. But in a sense, that's a crutch, just to be able to mask it. So we presented a rich example. The rich example had charged particles and 2 brane instantons on rigid associatives, circles of conifolds, and even we did the circle of conifold transition and the associated U1 Higgsing. We ignored the quantum G2 moduli space, of course. The big technical issue for non-abelian gauge symmetry and massless charge matter is that you don't have calibrated 2 cycles. So if you're getting an M2, a massive charged particle from wrapping an M2 brane on a 2 cycle, and you can't reliably take that 2 cycle to 0, how do you get a massless particle from it? Massless charge matter. Yeah, sorry. Non-abelian gauge symmetry and massless charge matter. It just gets really long to write that over. It's also not helpful if I don't tell you what it is. So thanks for asking. So the proposal was to collapse, rather than collapsing 2 cycles, which you can't do in moduli because they're not calibrated, collapse the things that you can collapse, which are associatives and co-associatives. There's a math trick and there was different physics associated with that, sort of 2 perspectives on it. And in this Coulomb branch story, we took rather general physics arguments and a fact about G2, this Joyce lemma, and what it led to was a standard vibration picture using very minimal arguments. And also 3 cycles to collapse, these vertical 3 cycles. And finally, the non-abelian dream is to use the K3 vibration and in a sense have K3 Higgs branches, which I can say more about if you're interested in, and to unhiggs those guys. That is still to be done for technical reasons. All right, so that's it. Thanks a lot.
Any questions?
So what is the upper limit to the 50 million? Why aren't there infinite many? Just because they didn't construct them, or?
Rumor has it there are more now. Rumor has it there are more now, but they have not been published yet. In fact, the full list hasn't been published anywhere. It's just people saying in their paper that they found 50 million.
But there's no particular reason why we would say it's a finite number.
I expect this number to grow in the coming years.
But it'll still be finite if you're constructed by Calibrations.
There's no finiteness theorem on Calabi threefolds.
So for, well,
That's what I was thinking.
no
Yeah.
theorem, but-
Pardon?
There's no theorem, but maybe an expectation.
There's no theorem, there's an expect, there is, well, it's a different case. There are a finite number of elliptic Calabi threefolds, but yeah, it may be an expectation. I think the feeling is that perhaps there's a finite number, but certainly, okay, good. So the point was made earlier that this is a special type of G2 manifold. So of course we expect that there are far more general types of G2 manifolds. I believe that. But even within this class, I think that there's going to be more appearing in the coming years. And I have heard large numbers that are larger than 50 million, but I will not say it on video. So.
Any other questions?